Hi, and welcome to the second installment of DC circuits. Again, we're going to hit on some of the basic concepts you'll need to be armed with for DC circuits to make complete sense. The downside is that you may leave this video wanting a little more. Don't worry, the next video is going to wrap it all up for us, but you still need to get these basics down. The schematic symbol for a battery is a wider and smaller horizontal bar. This represents a single cell battery. More often, you'll see it with two cells connected in series, or one just above the other. This is how it's shown almost always, even if the device uses more than two batteries. What you'll see instead is a rating for the batteries in volts. Like in the case here, this is a 12-volt battery. You've probably also heard of 9-volt batteries. The batteries, like the cylinder batteries, the AAAs, AA's, C's, D batteries, those are all rated at about 1.1 or 1.2 volts each. What you won't see on a schematic is the plus and minus sign that I've drawn on here. It's incumbent upon you to remember that the positive side of the battery is the wider bar. The shorter one is the negative terminal. This is rarely ever drawn upside down, but I have seen it. But you just have to remember that the positive side is the wider bar. Let's first take a look at how a battery works. A battery is made of two different kinds of metal conductors that are separated by an electrolyte. The electrolyte pulls the electrons from one metal conductor and places them on the second. This creates an overabundance of electrons on that terminal. Remember from the last video, we proved that electrons repel each other, and so as more electrons build up on the plate, it builds up a pressure to escape. But there's no place for them to go, as the electrolyte only allows them to move in one direction. Remember that game where you'd blow up a balloon, but instead of tying it off, you'd let it go and it would fly around the room? That's because your breath filled the balloon from a normal air pressure of 1 to about 150, and while you held it, you kept that potential energy inside. That's the state of our battery when disconnected, a potential energy just waiting to be let go. And let us not forget that those electrons came from electrically stable atoms. Now those atoms have lost electrons, turning them into ions who desperately want to get electrons back so that they can be stable again. Now if we were to hook a wire up to one of the terminals, that force, that pressure, would just continue through the wire, because on a good conductor there is electrically no difference between the terminal and the end of the wire. A common tool of the engineer and the technician is the voltmeter. This tool measures that potential difference between two places in the circuit. You can think of it for now as a difference in the number of electrons, but remember, all those electrons want to push away from the terminal, and the anode wants to suck in more electrons just as hard. If we measured the voltage across the battery like this, we would measure about 12 volts, as you would expect. If you were to connect the voltmeter to the battery terminal and to the other end of a wire connected to it, what would you expect to read? The answer would be 0 volts, because from the terminal and the end of the wire connected to it, there is no potential difference. Like I said earlier, as soon as you connect a wire to it, that pressure goes right through the wire. So there would be no difference between the terminal and the end of the wire connected to it. Whenever the pathway for the electrons to get from the cathode back to the anode is open, it's referred to as an open circuit. If we were to connect the two terminals of the battery with a wire, we would create a short circuit. Don't do this. This would allow the free flow of electrons back to the anode, and of course that electrolyte is going to keep transferring electrons back to the cathode inside the battery as fast as it can. This will definitely kill your battery and may harm you or your working environment. Don't short out the battery. Here we added a light bulb between the two battery terminals. The lamp will stay lit while the battery still has power left in it. Speaking of which, why do batteries die? On the non-rechargeable batteries, it's because corrosion builds up on the internal terminals from contact with the electrolyte. This corrosion kills the free transfer of electrons and the battery becomes dead. I also want to point out on this image that the light bulb is labeled L1, it stands for lamp or light, and each successive light would have a different subscript, for example L2, L3, etc. This allows us to put notes about the part on the side of the schematic where they're out of the way, and to be able to find that part on the circuit board, which will also label all the parts. But it's unlikely that the circuit board layout will be anything like the schematic diagram. So we covered a lot of ground in this video, but here are the key points you have to take away. The positive terminal on the battery is represented by that wider horizontal bar on the schematic. The current actually flows from the negative side of the battery to the positive side. Voltmeters have to test across at least a single component to give any kind of meaningful information. And voltmeters will tell the difference of potential in volts. And in the next video, we're going to talk a lot more about what exactly the volt is. Alright, that's it for this video. Next time we'll cover resistance and current flow, called amps, and we'll really start putting this all together. I'll put a link to the first video in the description for those who want to start at the beginning of the series, and you know how this works. Hit like if you did, and click subscribe if you want to keep seeing more. Thanks for watching.